In this video, we'll look at some examples of bases of vector spaces. Get that document camera up. We could state this as either an example or a theorem. Let A be any invertible n by n matrix. The columns of A are a basis for Rn. This example shows that one vector space can have multiple bases. This result comes from the invertible matrix theorem. This list of 12 conditions are all equivalent. So in particular, if A is invertible, 1, then the columns of A are linearly independent, 5, and the columns of A span Rn, 8. So a linearly independent spanning set is precisely a basis. In particular, the standard basis vectors of Rn, which we defined before we ever defined a basis when we were talking about linear transformations, are the columns of the identity matrix I. I is invertible. As a matter of fact, the identity matrix is its own inverse. So this previous example says this is a basis. And if we're looking at the 3 by 3 matrix, for example, if we're looking at R3, the first column of I is E sub 1. The second column of I is E sub 2. The third column of I is E sub 3. A completely unrelated example. Let's look at the polynomial space P sub n. This also has a basis referred to as the standard basis. The polynomials 1, x x squared up to x to the n. Why is this a basis? Well, to be a basis, it needs to do two things. It needs to span P sub n. So any polynomial in P sub n needs to be a linear combination of these alleged basis vectors. Well, a polynomial in P sub n has this form. Some of these a sub I might be 0. Remember that P sub n is polynomials of degree less than or equal to n. Maybe this is a second degree polynomial and all of these terms are 0. But be that as it may, this is a linear let's put in that first basis vector. This clearly is a linear combination of these vectors. So check on this. What about linear independence? So to be linearly independent, the following equation needs to have only the trivial solution. Three bars denotes identically equal to. And what we're trying to make clear with this notation is that this is not some equation we want to solve by using the quadratic formula or factoring or using a computer algebra system. This is identically equal to 0. So in particular, this has to equal 0 for every value of x. And if any of these a sub I are non-zero, this polynomial has a degree. Like if this a sub 2 is non-zero, this polynomial is at least degree 2. Any polynomial with a degree can only have finite many roots. A polynomial of degree n can have at most n roots. For example, a polynomial of degree 2 can have at most 2 roots. For this polynomial to equal 0 everywhere, to have infinitely many roots, it can't have a degree. The only polynomial without a degree is the 0 polynomial. To make this the 0 polynomial, then all of these a sub I have to be 0. So the only way for this equality to hold is if all of the a sub I are 0 and we're golden. That's precisely the definition of linear independence. So this is a linearly independent spanning set, hence it's a basis. In this video, we've seen some examples of bases. We'll see more organically as the course progresses.